Hey everyone, in this video we discuss the principal values and principal directions, which are the same as the eigenvalues and eigenvectors. And we have the scalar invariant of a tensor field. So let's get started by the principal values and principal directions and discussing their properties. We already discussed that for a real tensor, like a stress tensor or strain tensor, if it is symmetric, so we have three eigen values or three principal values. So if you have symmetric tensor, so for a symmetric tensor, for a real symmetric tensor, so something like the stress or strain tensor, so there exists three eigenvalues, or we call them principal values. So we have three eigenvalues, and we already discussed this in the previous video. So now, and we know that for each principal value, we have a corresponding eigenvector or principal direction. So now we are going to go case by case and see how these principal values are correlated together, and they're all, as well as their their principal directions or the eigenvectors. So I use the terminology principal values and principal directions instead of eigenvalues and eigenvectors here. But before that, we want to we want to prove something, and it is this statement here. So we first prove that, of course, for a mutually perpendicular system, as we already said that we in this course we discuss three mutually perpendicular coordinates, Cartesian coordinate system. So this cannot be applied to some coordinate systems which are not perpendicular to each other. So we first prove that if we have three principal directions, they're mutually perpendicular. We first prove that if there exists three mu, there exists three principal directions. They're mutually perpendicular. And to prove this, so we may start from here that if you have, let's say, t n1, so you can write it as lambda n1, and if you have t n2, you can write it as lambda n2. And let's write here that if you have tn1, so it has not the same eigenvalues as tn2. So we specify this by subscript 1 and this one by subscript 2. So we distinguish between lambda 1 and lambda 2, so they are not equal to each other. So if we take this one and if we dot it, so if we dot product it with n2 here, so we have n2 dot tn1, which is equal to, it is n2 dot lambda 1 n1. So you can take out this, let's say, lambda 1, because it's a scalar value, so you can take it out here. It becomes lambda 1 and 2 dots and 1. And if we do the same here, so we multiply both sides of the equality with dot and 1, so we have n1 dot t n2 is equal to n1 dot lambda 2 n2. This is a scalar, you can take it out, so this is lambda 2 n1 dot n2 here. So we have these two equations here, this one, and the other one is here. So now for a symmetric tensor, because we already are talking about a symmetric tensor. So for a symmetric tensor, T is equal to T transpose here. So now we have these two equations here. So this one is n2 dot t n1 is equal to lambda 1 n2 dot n1, and the other one is n1 dot t n2 is equal to lambda 2 n1 dot n2. So I can rewrite this as n1 dot t transpose n2, which is equal to lambda 1 n2 n1, and since t is equal to t transpose, so n1 dot t n2 is equal to lambda n1, this is dot, n2, this is n2 dot n1. So we have two equalities here, so we can subtract them from each other. So we call this 1 and this 2. So 1 minus 2 gives. So this cancels out with this one. So we have lambda 1. Oh, sorry, this is lambda 1 here. And 2 and 1 minus lambda 2 and 1 dot n2. And you know, n1 dot n2 is equal to n2 dot n1, because this is a scalar, finally, this dot product. So we can substitute it with n2 minus n1. So I can rewrite this as lambda 1 minus lambda 2. Sorry, this is equal to 0. So I can write this as lambda 1 minus lambda 2. n1 dot n2 is equal to 0. And we know that lambda 1 minus lambda 2 is not 0, because lambda 1 is not equal to lambda 2. We already discussed this, and make this clear here, that lambda 1 is totally different from lambda 2. So therefore, we have this n1 dot n2 is equal to 0. Therefore, we can say that n1 is perpendicular to n2. So we can do the same with, and with the per n1 n3 and n2 n3, and we all get for each equation we get the same result. So here we now got this point here, that if there exist three principal directions, they are mutually perpendicular. So now we discuss over the values of lambda and their principal directions. So we have different cases here. So we have case 1. So in this case, we have lambda 1 not equal to lambda 2 not equal to lambda 3. So you have three different principal values. So in this case, basically, you have at least one of the principal directions. One of the principal directions are perpendicular to each other. So we already discussed this. So as already shown, of course, above, uh, at least one of the principal direction, or we call them eigenvectors. Let's like write it here. Eigenvectors are perpendicular to each other. So the next case is case 2, where we have this lambda 1 equal to lambda 2, which is not equal to lambda 3. So two of these values are equal to each other. So for this case, we have let's say, for example, lambda 1 is equal to lambda 2 is equal to a lambda here. So you can write Tn1 is equal to, instead of writing lambda 1 and 1, we can write lambda and 1, and Tn2 is equal to lambda 2 and 2, which is equal to lambda and 2. So here, if we say we have two scalar fields, so for any scalar alpha and beta, so we have something like T alpha and 1 is equal to lambda alpha and 1, and we have T beta and 2 is equal to alpha beta and 2. So if we sum these together, we will have T alpha and 1 plus beta and 2 is equal to lambda alpha and 1 plus beta and 2. And here, this is the eigenvector here. So we can say that for any infinite number of principal directions, we have, because alpha and beta, they can employ any kind of scalars that we want. For example, it could be plus minus 1 or minus plus 1, or other kinds of values which actually meets this alpha squared. If you remember those cosine squared theta, cosine squared gamma, cosine squared, I guess it was beta, something like this. So if as long as this is equal to 1 and this scalars actually meets this equation here, so they can be any value. So there will be infinite number of n1 and n2s, for example, like this, or for example like this, or any kind of n1 and n2 vectors, which infinite number of them, which create a kind of let's say a plane, let's say plane P, where we have this the third one, because here we have lambda 1 equal to lambda 2, so it is not, they're not equal to lambda 3. So this is n3 here, which is perpendicular to this plane. So we can recap this as, so if this occurs, there exists infinite number of principal directions, which form a plane here, alpha n1 and beta n2, and n3 is, of course, perpendicular to this plane. So basically it becomes like if we have the principal directions, then we have n1 as plus minus e1, n2 as plus minus e2, and we have n3 here, which is perpendicular to each kind of, any combination of n1 and n2, which is here. So this is equal to alpha e1 plus beta e2 here. And I'm not going to put plus minus here because alpha and beta, they both can be positive and negative. So I just put plus here. And there exists another case where lambda 1 is equal to lambda 2 is equal to lambda 3. And for this, basically any vector is a principal vector. So in other words, you have infinitely sets of, mutually perpendicular principal directions to each other here for this case. We already had this case in let's say, example example 2, 22, 1. All right, so this is all about the principal values and principal directions and how to treat them in mutually perpendicular, Cartesian coordinate system. But we can also write these principal directions, principal values, sorry, in, let's say, in a matrix form. So, as Book said, matrix of a tensor with respect to principal directions. So you can easily write the components, let's say the spectral representation, what is called. So this is called a spectral representation of a tensor, where you can write, for example, T, the tensor T in a matrix form of the principal values. So we have lambda 1, lambda 2, and lambda 3 on the diagonal, and the rests are 0. But how you can write this? So if you have T11 of this, let's say, this tensor here, so you can write n1 dot tn1, which we already use this as for representing the components of a tensor. So you can substitute tn1 with let's say lambda n1, and you can take out this lambda here because it is a scalar. So n1 dot n1, and this is basically 1. So this is, so if we call this lambda 1, so this becomes 1, lambda 1, and this magnitude here is 1. So for example, if you have t to 2, it becomes n2 dot t n2. So you have n2 dot lambda 2 n2. So you can take out this lambda 2, n2 dot n2, this becomes lambda 2. So if you have t3 2, this becomes n3 dot t n2 here. And if let's suppose that you have lambda 3, for example, here, so n3 dot lambda 3 n, or maybe lambda 2 n2. So you have lambda 2 and 3 dot n2, which this become because they are mutually perpendicular, so this becomes 0. And that's it. Okay, so you can recall this as from your strengths of material course, where you had the Moore circle, where you had the principal stress, where you had sigma 1, sigma 2, and sigma 3 here. So these were your principal stresses. And if you remember, for example, you had the Moore circle here, sigma tau, and you had the 3D Moore circle. You had a long, for example, for the plane stress situation, you had something like this. And so maybe for the plane strain is better to say, because I wanted to show you something. So you had three stresses here. So for example, it became something like this. So you had sigma 3, sigma 2, and sigma 1 here. You know that sigma 1 is larger than sigma 2, larger than sigma 3. And you have to know that the Moore circle is not the same as, is not the same for the plane stress and plane strain situation. For the plane strain situation, sigma 1, sigma 2, and sigma 3, we have these values, but for plane stress, sigma 3 is basically 0. This is the minimum value, and this is the maximum value here. So we exploit the same, the same terminal, the same concept here to mention that these lambda 1, lambda 2, and lambda 3 values, they can be written in a form that a lambda 1 is bigger than lambda 2 is bigger than lambda 3. So these are the principal values, and we use the same lambda 1, lambda 2, and lambda 3 to find the principal stress as well as the principal strains here. All right, so let's say that if we have this tensor here, so we can show that that the tensor T, so we can show that a tensor T so includes a maximum and a minimum values that the diagonal elements of any matrix T can have. So first we have this, let's say, E prime vector here, where we have alpha and 1 plus beta and 2 plus gamma and 3. And if we use the transformation here to transform it to another kind of, let's say tensor, so we have T prime 1, the transform tensor. You write E prime 1 dot T E e prime 1 here. So we said that we are supposed to write it as a row vector like alpha, beta, and gamma, and then we have this t here. So this is lambda 1 0 0 0, lambda 2 0 0 0, lambda 3. So this will give you what you have here as alpha, and sorry, you have to also write this as let's say a column vector here, so alpha, beta, and gamma, because this is either you write it like you put this in here as a row vector, or you write it as a column vector here. So you have alpha, beta, gamma times this, so it becomes alpha, so it is a 1 by 3, this is a 3 by 3, so we will give 1 by 3. So you have alpha lambda 1, beta lambda 2, gamma lambda 3 times alpha beta gamma, which is alpha squared lambda 1 plus beta squared lambda 2 plus gamma squared lambda 3 here, lambda 3. So if we assume that lambda 1 is larger than lambda 2, it is larger than lambda 3, so this is the maximum and this is the minimum. So if we multiply lambda 1 by, let's say, alpha squared plus beta squared plus gamma squared, so we know that these are the angles which are made by by each kind of these unit vectors here. So if you have, for example, this vector here, so you have alpha, which is created by E1, you have beta created by E3, and you have gamma, which is created by this E3 direction here. So the squared of each, each cosine of each, and the summation of all of them is equal to 1. So alpha 1 plus beta 2 plus gamma 2 is equal to 1. You can remember this from even high school. All right. So now you can see here that this is basically bigger than this value here, alpha squared lambda 1 plus beta squared lambda 2 plus gamma squared lambda 3. And this is actually means that lambda 1 value is bigger than this t. This is actually the representation of t prime 1 1, right? So you can say, therefore, lambda 1 is bigger than t prime 1 1. And using the same strategy, you can write that here, you can write this lambda 3 here times this value. So if I just copy this from here and paste it here, so you can write that this is larger or equal than lambda 3 times alpha squared plus beta squared plus gamma squared, which is basically 1. So this is again t prime 1 1, which we got from here. So we can say that t prime 1 1 is larger than lambda 3. Therefore, we can conclude that the maximum principal value of a tensor T is the maximum of the diagonal elements of the matrix T, and the minimum value, again, it corresponds to the minimum value of the diagonal element of the matrix T, and T here is this, let's say, this matrix here. So we can say that's the same, let's say, concept from matrix can be applied to the tensor. So if you have a diagonal matrix, and if you sort them out like lambda 1, lambda 2, and lambda 3, where lambda 1 is the maximum and lambda 3 is the minimum, we can write that we can say that the principal values of t here are lambda 1, lambda 2, and lambda 3. And as I said, this is quite useful in finding the principal values of stress and strains, where we can use in, for example, in, let's say, a stress criterion for materials, for metallic materials like the von Mises or the Tresca we use, because in those kind of criteria, we work with the principal values. So the last topic is the principal invariants. The principal scalar invariants. And as you remember, we already said that if you have the t n1 is equal to lambda n1, or let's say n here and n, we said that you can write this, you can rewrite this as t minus lambda I n is equal to 0. And this actually gave you the determinant of this tensor here, gave you the characteristic equation. So we can write that the characteristic equation here was Tij minus lambda delta ij is equal to, determinant is equal to 0 here. And if you write this, you will get something like lambda 3 minus I1 lambda squared plus I2 lambda minus I3 is equal to 0. And these are basically called these I1 and I2 and I3, these are called the scalar invariants. And each are equal to these expressions here. So I1, for example, is equal to some of the diagonals, the elements on the diagonal of the tensor. So this is equal to TII, which is the same as the trace of the tensor T. And I2 is nothing but, let's say, if you have T11, T12, T13, 21, 22, 23, 31, 32, and this is 33. So we basically start with 1 and 1 with 1 and 2. So we remove this from here. So you have here written. And then we next get rid of this, and then we have this, and next we remove this, and we have the determinant of this here. So I will write it here so it becomes clear. So we have the determinant of you will get something like this, which is equal to half of the TIITJJ minus TIJTJI. So if you write this in the tensorial notation, this is the initial notation, you'll get half of the, here you have two traces, so you have the trace of T squared minus, and here you can see that this is the trace of T squared because we have T dot T, so this is TIJTJI. So this is equal to the trace of T, so this is T squared. Because this is equal to, for example, it gives something like TII squared. Trace T squared. And the last scalar invariant is I3, which is basically the determinant of the whole tensor 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3, which is basically the determinant of the tensor, let's say, T. So these are called the principal, let's say, scalar invariant of the tensor T, I1, I2, and I3. And I1, I2, and I3 can also be written in terms of, eigen values or principal values. So scalar invariance in terms of eigenvalues or principal values. So they are I1, lambda 1 plus lambda 2 plus lambda 3. So that means if you have written a tensor like T in this form, in this fashion, so you found lambda 1, lambda 2, and lambda 3, this is the trace. So I1, the first invariant, is the trace of the tensor. So it is lambda 1 plus lambda 2 plus lambda 3. Then I2 basically becomes lambda 1, lambda 2, plus lambda 2, lambda 3, plus lambda 3, lambda 1. And this is because some of the terms here, they become 0. So we have 0, 0 here, 0, 0 here, 0, and 0 here. So you will only have lambda 1, lambda 2, plus lambda 2, lambda 3, plus lambda 3, lambda 1, lambda 3 here. And finally, you have I3, which becomes lambda 1, lambda 2, lambda 3, so their product. Because here, the rest of the terms are 0, the off-diagonals are 0, so you have only lambda 1, lambda 2, and lambda 3, and the determinant is lambda 1 times lambda 2 times lambda 3, and the rest they become 0. And that's it.
All right, everybody. So I thought that maybe having a demonstration for this video is also somehow essential, so it provides a good insight into the problem. First we start by importing the SymPy package here into the Jupyter notebook, and we define the tensor components here from T11 to T33 here. And we first start with the principal scalar invariance of the tensor T. Here we define the tensor T as the one you see here. And according to the equation 225.1 of the book, the characteristic equation is what you see here, and we already discussed over this. in order to extract this characteristic equation for this tensor, so as I said, we defined this beta instead of lambda because lambda is a reserved word in Python. So I simply write beta equal to sp, which stands for SymPy package here, because I imported it as sp. So that symbol beta. So I define it here as a as a symbol. So beta is a symbol. So it will be treated as a symbol here. And I have this method here, charpoly, which is the characteristic polynomial for beta. And if I factor out and run everything here, you will see that I get something like this equation here. So I have beta instead of lambda, so I have beta cubed plus. So if I factor out this minus, so it'll become the trace of the tensor for the coefficient of beta squared. And then I have this expression here, as we already mentioned in let's say as you in the notes, and it is the equation 2.253 of the book, and then the rest is and which is the coefficient for beta, and the rest is basically the determinant of the tensor here, which is the same as the determinant of the matrix. So the invariants, if we want to calculate them just separately, so we have I1, which was the trace. So if I do this by sp.trace, the trace method here, so I will have T1 plus T2 plus T3, which is basically the trace of T. So if you write it in initial notation, it becomes TII. And the second invariant was half of the trace of the tensor cube squared minus the trace of trace of the t squared. So if I do it and I use the simplify method here, I will get something like this, which is the same as the one you see here, the coefficient for beta. And the third one is basically the determinant of the tensor here. As you can see, it is here from here. That's it. Okay, so if we write the scalar invariance in terms of the principal values, so let's say lambda 1, lambda 2, and lambda 3. So we have, for example, something like this. So we only have the principal values. So the rest of the, the off diagonals are 0. So if I write the characteristic equation, so finally you should get T1, T2, and T3 because they are basically the, let's say, uh, the principal values. So we have the trace of the tensor as I1. These are the equations from 225.5 equation in the book. And if we simplify, and if we have I2 in the second invariant, it becomes this. So you can substitute T1, T2, and T3 with lambda 1, lambda 2, and lambda 3 in equation 225.5 of the book. And then you have this, let's say, the determinant of T, it becomes the product of T1, T2, and T3.